I'll do that. Okay, actually no, it's so that's good. I will resume recording. Make sure I have my water with me just in case. I do. I will resume
recording in progress.
That's recording. And okay. There we go. Good to go. Camera's crooked, as always. Everybody can see me on my screen? Say hello? Okay. So, welcome everybody to the official MTH514 final exam tutorial. Yeah, it's official. And today I have some, as I just said, I have some questions planned from chapter 5, which is joint distributions, chapter 6, which is multiple random variables or just moment generating functions, and then chapter 7 with the central limit theorem, and then chapter 11 with the Poisson process. Thank you very much. It definitely says our current school name on it, the current one. And yeah, so those are the chapters that we're going to talk about today, because that's the chapters that are going to be focused for on the exam. So yeah, I don't know if there's anything else to say before we get into it. Oh yeah, there is something else to say before I get into it. Of course, as always, you can find my notes on my website, www.tutor.ca/notes. So I have notes for this course. I finished them at the end of the course. So that's not what I meant to do. What did I just do? What did I even click to make that happen? I don't know what I clicked to make the tab switch. Anyways, there's my notes. And I'll be making reference to them throughout life. Okay, so the first thing, actually, let me leave the chat open. The first thing we're going to do is we're going to talk about chapter 5. I think a good place to start is this question, and then I have a suggestion. Someone sent a suggestion in. So this is a lab problem. I'll work through it. Oh yeah, actually, before we start, let me make a guess for what's going to be on this exam. Okay, this is my prediction. So my predictions are a Poisson process question. Not too surprising. He said that would be on. Then he said bivariate normal distribution. Not surprising either. He said that would be on. What else? Someone's in the chat here. He said last lecture, 1 Poisson, 1 bivariate, and then 2 random variable question plus whatever else he planned. Okay. So he confirmed that there's going to be another, there's like just a joint distribution one? Probably. Joint distribution, just in general. So what exactly does that mean, joint distribution? Well, what are some things he could ask? He could ask like the joint PDF, marginal PDFs, blah, blah, blah. To be honest, he could ask something like this. So this first question, kind of covers that. Find the appropriate value of C, marginal PDF, are X and Y independent, and find this probability. Yeah. But probably more. I think there will be, I don't know. I wouldn't be too surprised if there was a moment generating function. But they're not super wild questions, but they're like kind of have to know what you're doing. They don't take that much math though, so they're okay. So we'll do an example of that, and then central limit theorem. I know there's too many questions now, but that's probably my guess of what's going to be on this. Maybe one of them won't be. Yeah, everything from chapter 7 exactly that'd be CL. That's what I mean by CL. Exactly. So yeah, I agree. So yeah, we're gonna go through this. We're gonna try to prepare for this. Once again, forgive me if there's any hiccups on the way. I'm a little behind on my practice, but this I know. This question I know at least because I did it today. That's how I know. So anyways, let's begin. This is from the lab. So yeah, we're going to do kind of a mixture of lab problems. Actually, I have quite a few lab problems chosen, then some textbook problems if they're interesting, lecture problems, kind of just all over the place. Which I understand for some people is going to be repeats, but if it's, it's it's good repeat, then it's good to do. Let x and y be two random variables with the joint PDF given by this expression. Find the appropriate value of c and the joint CDF. Find the marginal PDFs of x and y. Are they independent? And then find this probability. So let's start with finding the c value here. Right? That's what it's asking us. So as with every PDF, like the definition of the PDF is that if you integrate it over the entire area that it exists, you should get 1. Every PDF works like that. So if we just quickly draw a sketch, and the sketch is going to be helpful. Right? So if we draw a sketch of what's going on here, if x is greater than 0, so that way, and if y is between 0 and 2 pi, so this is kind of the zone that we're talking about here. This is the region where this PDF exists. Everywhere else is 0. And this goes forever, right? This goes forever this way. Just x greater than 0, y is between them. So our integral is going to be over this region, right? It's going to be a double integral because there's 2 variables, double integral. And I'll do, of the function, cx e to the negative x squared over 2 dx dy. So x goes from 0 to infinity, y goes from 0 to 2 pi. Right? And we know this has to be equal to 1. Or just for simplicity, like just for ease of writing, I'm just going to say 1 equals this. Because that's integrating it over the entire domain that it exists in. So let's do it. We got to integrate now. So the c can come out, right? So it's going to be 1 equals integral. Well, okay, so I'll move the c out. So it's going to be over c here, right? Because the c is going to come out and you divide it by c on both. I don't want to write the whole line again. Okay, and then we have this integral. 0 to 2 pi, integral 0 to infinity, x e to the negative x squared over 2 dx dy. So this doesn't have any y in it, right? So this whole thing is a constant to this integral. So this can just come out to the side. So it's basically just 1 over c, integral 0 to infinity, x e to the negative x squared over 2 dx, integral 0 to 2 pi y. So 1 over c, multiplying here. That's just 2 pi. 2 pi minus 0 is 2 pi. And then this integral we have to figure out. So it's 2 pi times this integral 0 to infinity of x e to the negative x squared over 2 dx. So this integral here, we can solve. It's kind of similar to like what we had on the previous midterm. We had kind of a question like this. Kind of. So we're going to do, this one's just a u sub. So we're just going to sub in u equals negative x squared over 2. Du is negative x, right? Because it's negative 2x over 2, which is negative x. Yeah. So this is what we're going to get. We're going to get 1 over c equals negative 2 pi integral 0 to infinity of, so what's this going to be? This is going to be e to the u du, which is 1 over c, negative 2 pi. Integral of e to the u is just e to the u, evaluated from 0 to infinity. We get 1 over c, negative 2 pi. So this is going to be e to the infinity. Oh, e to the infinity minus, oh, sorry, not e to the infinity, sorry. E to the negative x squared over 2, evaluated infinity. So let me just, actually, I'll write it like this. I'll still write it like that, just substituting back in u. And this is now 1 over c, negative 2 pi e, so e to the negative infinity minus e to the 0. So that's 1 over c minus 2 pi times 0 minus 1, which is, it's going to be 2 pi, right? Because the negative and the negative are going to cancel. So finally, we can conclude that c is 1 over 2 pi. So not a wild integration. Just have to do a little bit. Doing that a lot today. I don't know. Just have to do some u substitution, and then remember to put the u back in. I forgot to. But anyway, we get our c value is 1 over 2 pi. Perfect. So that means that our PDF fx now of x is 1 over 2 pi and it was x e to the negative x squared over 2. And this is valid when x is greater than 0, right? And y, well, yeah, and y is between 0 and 2 pi. But of course, that's not there, right? And it's just 0 otherwise. Great, so we found our, sorry, this is fxy. But it's not dependent on y, right? It's just, like, there's no y in here. Okay, so that's the appropriate value of c and the joint CDF. Oh, sorry, not and the joint, and now we have to find the joint CDF. So now let's find the joint CDF. So the joint CDF is fxy xy. And so the way we're going to do this is we have to break up our region into a bunch of different possibilities. So remember, this is the probability that x is less than x and y is less than y, right? This is what we're trying to find. And so in our region, right, if I draw that region again, that's 2 pi. What you want to imagine, this is the best way to visualize it, I think, right? Is imagine like an arbitrary xy point, right? Imagine like an arbitrary, like, this is the point right here. This is like x naught, y naught, right? The probability in this square that I'm drawing, right, in this section, right, is the CDF evaluated at this point, right? Because you're looking for all the you're looking for the probability that x is less than x, so that's this entire section, and y is less than y, so that's this entire section. And so the intersection of those two is this zone right here. So the probability that's contained within this zone is f x, capital F x y, x naught, y naught. So what we do is we just kind of drag that around, right? So if I move it here instead, right? So yeah, if I move it here instead, let's say, then the actual relevant probability, let me just want to get rid of this just so that's easier to drag around. So the actual relevant probability is this little zone right here, right? That's the probability that we account for, right? Because it's in this zone and it's in this that section. So again, that's how we determine the different zones of our CDF, right? We just sort of drag this little thing around. So if x is less than 0, then it's 0, right? If x is less than 0, then it's 0. So there's no probability in the zone if x is less than 0. So f xy xy, I'll just say f xy equals 0 if x is less than 0. Well, not equal. Well, I guess technically equal to, but I'll just say that. If x is less than 0, we have that. If x is greater than 0, but y is less than 0, right, then we still have no probability. Right? So x is greater than 0 here, but y is still less. So I'll say or y is less than 0. But if x is, let's say, greater than 0 and y is between 0 and 2 pi, so if x is greater than 0 and y is between 0 and 2 pi, that's kind of like what we're describing right here, right now, right? Then our relevant probability is the integral over this zone right here, right? That's the zone that's part of our CDF. Because again, the cumulative is like all the way up to that point. Every x value lower, every y value lower. But there's no probabilities here, right? It's probability 0 in everywhere else except in this little blue triangle, rectangle. So f xy is the double integral over that zone of our fxy xy dx dy. And now what's that? What is that zone? Well, that zone, the x value goes from 0 to x naught, or whatever, we'll just call it x, 0 to x. And the y value goes from 0 to y. And this is assuming that x is greater than 0 and y is between 0 and 2 pi. Okay, but what if we're not in that zone, right? So what if we move this up like this? What if x is still greater than 0, but y is not between 0 and 2 pi? Well, then the relevant probability is this zone right here, right? That little rectangle right there. That little rectangle. And what's that integral? So that's if, right, this. If, doesn't one of those dx's need to be a dy or no? Oh, yes. It's not dx, dy. Oops, spun my mouse around. Yeah, x goes from 0 to x, y goes from 0 to y. Yeah. So if x is greater than 0 and y is greater than 2 pi, then our integral, our fxy, is the integral is going to change, right? Still integrating the same thing, fxy, xy, dx dy. But now, okay, so x goes from 0 to x still, right? X goes from 0 to x. Y goes from 0 to 2 pi now. It doesn't go all the way to y, right? We don't have this little, that's not part of the probability. It's probability 0 then. This function is 0 in that zone. Great. And then that's actually all the cases basically, right? Because there's not really another case. Either like you could imagine like if this went far away this way, I guess I shouldn't bring that with me, should I? No. I think OneNote's not going to like me now. I'm trying to move many things at once. Let's just reconstruct it over here. Probably some way for me to group it together. Is there a group? Group. There you go. Perfect. So, yeah, probably Control H also does the same thing. So if I were to move it more this way, I'm never going to get on the other edge of this rectangle because it's infinite, right? This zone goes infinitely this way. So this right here, that's still this case. Because the integral from 0 to x, and for x and y 0 to 2 pi, and that's still this third case. So in fact, yeah, that's it, right? You can confirm with what I wrote before. 0 to 0 to x. Yeah. So let's compute it now. I mean, it's not that much to compute, right? So we have this first zone, right? And then the next zone is this integral, right? So I'll just call this region 1, region 2, region 3. So just put it nicely here, fxy of xy equals, and now we have a piecewise defined function, so 0 if x less than 0 or y less than 0. Then I'm going to put something else here. So let's figure out what I'm going to put there. That's the integral 0 to x, 0 to y of whatever our fxy was, right? Which was 1 over 2 pi x e to the negative x squared over 2 dx. Right? So I got to work this out. What is this? So the 1 over 2 pi leaves. Right? The 1 over 2 pi leaves, and okay, I'll just rewrite it. So, and dx dy. So 0 to y, integral 0 to x, x e to the negative x squared over 2 dx dy. Again, there's no y in this, right? So that's just a constant to that integral, so we can just take it out. So it's just going to be 1 over 2 pi integral 0 to y dy times integral 0 to x, x e to the negative x squared over 2 dx. So this is just going to be y over 2 pi, I mean. And then integral 0 to x, x e to the negative x squared. Which, like we saw before, is just a u sub. So I'm not going to do this a million times, but we'll just do it here. So u equals negative x squared over 2. So du is negative x dx. And so we get y over 2 pi integral 0 to x. And negative this, because the negative dx here. And this is e to the u du, which is negative y over 2 pi, e to the u evaluated 0 to x, negative y over 2 pi, e to the negative x squared over 2, evaluated 0 to x, negative y over 2 pi. And so finally we have, evaluating at x, we just have e to the negative x squared over 2. Evaluating at 0, we just have 1 minus. So there you go. That's the answer in this zone, right? In this zone. And that's if x is greater than 0 and y is between 0 and 2 pi. And then the last one, the last zone is the same integral, but it's the exact same integral, but it's just a 2 pi here instead. So it's going to be 2 pi over 2 pi, right? 2 pi over 2 pi e to the negative x squared over 2 minus 1. If x greater than 0 and y greater than 2 pi. So that's So that's just zero, it's just 1 there. Did I? Yeah, I guess I forgot a negative. Yeah. I guess this quantity will be negative. Will this quantity be negative? Yeah, this quantity will be negative, yes. Yeah. This will be negative, but then negative times. Okay, good. So there's our CDF. That is our CDF for this function, this down. Part B, find the marginal PDFs of x and y, or x and y independent. The marginal PDFs, part B, right? We want to find the marginal PDF fx of x, right? Which basically we're basically like looking for probability that like x equals x, basically. It's continuous, so that's 0, but along those lines. So we integrate all over the y values. So we're going to integrate our function fxy, our joint distribution, and we're looking for the x, so we're going to vary y, right? So y is the thing that's varying, and we're going to add up all those probabilities for all the different y's, and that tells us what our probability is for some particular x. So if for any arbitrary x, right? Let's say I choose this x value here. Y varies from 0 to 2 pi. So this is going to be 0 to 2 pi, the integral of this dy. So if I do that, it's going to be the integral from 0 to 2 pi of 1 over 2 pi x e to the negative x squared over 2 dy. But this is, that's of course just all a constant. So it's just going to be 1 over 2 pi x e to the negative x squared over 2 integral 0 to 2 pi dy, which is x e to the negative x squared over 2, because this is 2 pi times 1 over 2 pi. It's going to be 0. Give me 1. So that's our marginal PDF. That's representing the probabilities associated with just the variable f, which we extracted from the joint PDF. And fy of y is the integral of fxy dx. Now, for any arbitrary y value, what does x vary between? 0 and infinity, right? 0. So this is the integral from 0 to infinity. One thing I forgot to mention is the bounds on this, right? So when I chose that arbitrary x value, I assumed x was greater than 0, right? I assumed x was greater than 0. So that counts here. X is greater. Technically equal to, I guess. Okay. So now here's our y value one. So for the y, we're varying x instead, right? Y is staying constant. X is the thing that's varying. So we're going to integrate 0 to infinity of 1 over 2 pi x e to the negative x squared over 2 dx. So this time is dx, so it's 1 over 2 pi integral 0 to infinity of x e to the negative x squared over 2 dx. We saw earlier, right, that this integral turned out to be 1, right? Turned out to be 1, because it's 1 over c equals 2 pi times 1. Over here we had 1 over c equals 2 pi times that whole integral. So that whole integral is 1, which is what we have. This is also 1. This equals 1. I don't want to do the whole thing again, but equal to 1. So the answer is 2 pi. 1 over 2 pi. That's the whole marginal PDF for y. So now that's it. And then y has to be between 0 and 2 pi. I don't have a variable there, so it doesn't really matter, but technically. Now the question is, are they independent? Well, independence means that fxy, the way to check this is it true that fxy of xy is equal to fx of x times fy of y? That's our question. And the answer is going to be yes. So I'll just switch the order. Whatever, I won't switch the order. X e to the negative x squared over 2 times 1 over 2 pi, which is, of course, true. Right? This is true. So this is 1 over 2 pi x e to the negative x squared over 2. That's what this is, right? So this is equal to this. This is a true statement. Therefore, if anybody has any questions, feel free. Oh, there you go. I got a question. Could we logic that and say that if the entire area is equal to 1 and the height is 2 pi y, isn't in the equation for f y y? Y isn't in the equation. Oh yeah, since the entire area is equal to 1. The entire area of what? This thing here? Well, the entire integral over the area is 1. And the height is 2 pi of fy. Y isn't in the equation for fy. I'm not sure what you mean.
Like if we were to take, so we know that the entire area of fx of y, fxy is equal to 1. And the equation for fxy isn't dependent on y. Like there's no y in it. Therefore, we can just take the entire area, which is equal to 1, divided by 2 pi.
But what do you mean by the entire area? This area isn't 1.
It's not equal to 2 pi. It's not equal to 1. But
it's
like
not
the
equal to 1.
Entire area of the integral, right?
Which yeah, the integral. The integral is equal to 1.
Not just divide that by 2 pi.
Like, are you trying to generalize? Like, you're trying to generalize to?
No, I'm saying for this specific question, not like generally. I wouldn't recommend you do that. Like, I'm saying it works for this question.
No? Yeah, I mean, yeah, it does, because you get 1 over 2 pi for fy there. Like,
whether or not that logic is sound, though.
Yeah, I don't know.
Okay.
Yeah.
Cool. Thank you.
Because this integral is 1, so that's basically what's doing it. Is that when we integrate over with just the x, right? Just like if we were to integrate over our entire marginal PDF with just the x, we get 1, which means the y value is not actually contributing anything except a scaling that's happening. So I guess that scaling is kind of what you're getting at.
Yeah, exactly.
Yeah. But I'm not sure generally. Yeah, the height won't always be 2 pi. Okay, so that's that. They are independent. Now find this probability. Probability that x is greater than root y. Probability that x is greater than root y. So there's a few ways to do this, but square roots are kind of annoying. So I'll just turn this into the probability that x squared is greater than y. I'm allowed to do this because I know x is positive and I know root y is positive, so the inequality stays the same. Okay, so this is a little easier just to graph it. So now let's plot this zone, right? Let's plot this like what we're talking about here, right? So if I have x squared, this is the function x squared, right? We only care about where x is greater than 0, right? X is greater than 0. And we're saying y is less than x squared. So the y value, that's this zone here, right? That's this entire section. That's underneath the graph. But we also know that y is limited by 2 pi, right? So let's say that 2 pi is right here. Right? So that means that basically our answer, our zone that we're interested in, we're interested in this probability. Probability of this zone. Now let me draw that a little bit better. So yeah, there's two ways you could do this, right? You could instead do 1 minus probability of this zone, which maybe we'll do. Yeah, let's do it like that. Seems easier. So this is A, this is B. So probability of A is 1 minus the probability of B. So what's the probability of B? Probability of B is going to be a double integral, because this is region, right? So y varies from 0 to x squared. Or no, sorry, x squared to 2 pi. So it's 1 minus. And then x varies from 0 to, well, whatever this point is here, right? Whatever this x value is. What is that x value? That x value is some x value, which when you square it, you get 2 pi. So root 2 pi. So to root 2 pi. Of our function. right, of our 1 over 2 pi x e to the negative x squared over 2 dx dy. No, dy dx. So 1 minus this integral. Again, there's no y in here, right? So the y integral is just going to be, yeah. So the, like, it's a constant with respect to this here. Can you go over the integral bounds? Yeah, for sure. So I'm trying to integrate over b, right? Over b, this region here. So I just take some arbitrary element, some like differential length like this, right? And what does it go between? Well, first of all, the bottom is always going to be x squared. The y value is going to be x squared. And top is always going to be 2 pi. And then imagine dragging it left and right. The height will always adjust. So I can't animate that here, but the height will always adjust, like the width of it. So it'll be thin here, like a little small here, and then it'll get bigger, 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 all the way to full 1, or to full 2 pi. But it can vary freely between 0 and 2 pi, x, an x value of 0 and 2 pi. So the x goes between 0 and 2 pi, but that's the outside integral. The inside integral is the actual function, so it's between x squared, bottom, and 2 pi on the top. Let me explain better, I can, but no problem. So now I want to do this integral. So 1 over 2 pi comes out, and then it's just going to be, 1 over 2 pi comes out. Then I can't move this whole integral. Okay, so basically I can do this. I can do integral 0 to root 2 pi, integral x squared to 2 pi dy times x e to the negative x squared over 2 dx. That's what I can do, right? Because I can't actually take this out of the integral because there is an x in there. I can't take that out of this integral. This is going to be 1 minus 1 over 2 pi times, okay, so this is integral 0 to root 2 pi. This integral is just 2 pi minus x squared times x e to the negative x squared over 2 dx. It's gonna be a little annoying. It's gonna be a little bit annoying to compute. 1 minus 1 over 2 pi.
Sorry, Adam.
Yeah.
I think this integral is easier if you do it with y first and then x. If we're looking for part B, right?
Yeah, so it would be...
Then you get root x, and then because you have a squared in your exponential, it would like...
Oh, I see. Yeah, I see what you mean. I mean, I'm gonna have a root 2 pi there. Yeah, I see what you mean. I'm not gonna rewrite it, but yeah. That would be probably an easier way. Yeah. Thanks. So integral like that. And then it's gonna be x e to the negative x squared over 2 dx, and then minus, and then this is gonna be integral 0 to root 2 pi. Is there supposed to be a 1 over? No. And then x e to the negative x squared over 2 dx. Multiply the 1 over 2 pi in, 1 minus integral 0. Well, I guess we can do this integral, right? So I guess we don't, like, I guess integration by parts. Yeah, not integration by parts, but this is u equals negative x squared over 2 du equals negative x dx. I'm not going to touch this one. We'll see in a second.
You also forgot to distribute the x squared on the second one.
Yes, I did. U. And then 1 minus 1 over 2 pi. I guess I'll multiply the 2 pi in, so it's going to be integral 0. Or I guess that still has to be a bracket. Minus. Then it's going to be e to the u du. 0 to root 2 pi. And then this one, yeah, is it a double integration by parts? I don't really want to do that. So is there another way around it? No, I don't think there is, right? I think it's just... Because I know you can separate out x squared and x e to the negative x dx. U sub it but that would still be like, what do I use sub? I say u equals.
You could do negative x squared over 2, then rearrange to figure out what x squared is in terms of u, and then you could just do u e to the u.
Yeah, u e to the u. That's true. Or I can type it into Wolfram, and then we don't have to deal with it at the moment. It's up to you, guys. Yeah, is it just a single IVP? But then you're gonna have.
Can't you split it with x squared and then x?
X, yeah.
X squared over 2.
And I think that would be a double. That'd still be a double integration by part. Let's keep rolling. Yeah, I'm gonna just put it into Wolfram. If anybody has trouble with that, integrating that, feel free to ask me later. Tomorrow, I'll write out a solution for that. So anyway, so that's that. Okay, I'm just gonna type this into Wolfram. This one. Wolfram. So the integral is it's a single integral 0 to root 2 pi x cubed e to the negative x squared over 2. So I get kind of a annoying expression. So negative, what was the answer we got before? Let's see what it is here. What's the answer? Oh, we didn't write a final answer. Okay, I guess yeah, we didn't write a final answer. Okay, this is it's like we can do the integral, but it's gonna take a while. So anyways, let's just approximately do it. So this is gonna be I'm gonna approximate here. This is just 1.6421. Right. This integral, well, I can't type that in yet, so it's gonna be 1 minus. I'll put the negative in. So 1 plus integral 0 to root 2 pi e to the negative x squared over 2 dx minus, or no, not, sorry, I can't do that. I integrate and then do that. So this is going to be e to the u e to the negative x squared over 2 evaluated from 0 to root 2 pi plus 1.6421. And so yeah, so here's that happening, that thing right there, like that, right? So 1 plus, and then this is going to be some number. This isn't going to be a negative number. Minus 1. Oh, is there a problem? I missed the negative sign there. Damn. 1 minus, because I can't, this is going to be, this is certainly a positive number, right? And a positive number plus a positive number plus a positive number is a number bigger than 1. This is going to be a number bigger than 1. And that doesn't make sense. So, probability. So, somewhere is a mishap. And I think it's, well, one thing is I didn't divide by 1 over 2 pi. So, over 2 pi. I think it's like a negative sign is wrong. Is that integral? There's 2 integrals. 1 minus that. And why is this negative? That's a minus there because it's 2 pi minus x squared. Okay. I think it's right. So this is going to be e to the, yeah, as long as we set up the integrals right. Yeah, I'm not going to stress about it too much. So it's 2 pi over 2 minus 1. Yeah, okay, this might be right now then, because this cancels with that plus whatever that is, 1.6421 over 2 pi. Yeah, this is probably right. Assuming, I mean. So e to the negative pi plus 1.6421 over 2 pi. That's our approximate. Okay, there you go. So that's kind of the process here. Now, of course, you could also just integrate over the entirety of A. You didn't have to do 1 minus the integral here. You could also just, that's how I did it originally, is I just integrate over the entirety of A. It's not that much harder. It's not even harder, actually. It's same amount of difficulty. You just have an infinity. But to be honest, that actually makes things easier probably because e to the negative infinity is 0, so it's convenient. Okay, so there's that question done. So that's dealt with this whole section here. I think maybe let's talk about moment generating functions now, just because they're interesting and they're not that hard, and I think it's nice to talk about. I feel like we won't talk too long about it. And then yeah, okay. So let me walk you through a little bit what the moment generating function is. Like we won't do an example just first. Like let me just kind of explain it a little bit here. So the idea of the moment generating function is if we have some random variable x, which is kind of complicated, maybe the distribution is complicated here, then we can find the moment generating function of it, mx of s, right? And it will generate all of the moments, which is the expected value, the expected value of x squared, x cubed. And these are all statistics which are interesting for, I don't know, practical situations. I don't know the practical situations, but apparently they are. So it's good to find like the expected value of x, the expected value of x squared, the expected value of x cubed. These are all relevant in some way to some sort of study. I don't know the exact examples, but so the moment generating function generates all of them for us. So let me explain why. The definition of the moment generating function is it's the expected value of e to the xs, right? So what's going on here? Well, remember that, yeah, sorry, e to the xs. Okay, that's the definition of the moment generating function, and it comes with a property. The reason it's like why does this generate the moments for us? Because if you take the moment generating function, right, and you take the nth derivative of it, ds to the n, evaluate at s equals 0, you get expected value of x to the n. But why? I mean, that seems like so unrelated, right? Like it's just an exponential. Like, so I can just show it's not that hard to show. So if I want like the expected value of x to the 50, I take the 50th derivative and evaluate at s equals 0. But usually we just choose n equals 1 or 2 or 3. I've never done 3, but it's not that hard. So 1 or 2. So let's see why. So let's look at our definition here. Moment generating function mx is the expected value of e to the xs. So let's look at our Taylor series here, right? The Taylor series of e to the xs is the sum. K goes from 0 to infinity of it would be xs to the k over k factorial. That's just the definition of e to the as a Taylor series. I'll rearrange it a little bit here. Just a little bit. So it's the sum. K goes from 0 to infinity of x to the k, s to the k over k factorial. So we've kind of rearranged it here just slightly. And remember that the expected value is linear. So this is just a long sum, right? It's just a sum. So if you take the expected value, it's just going to be the expected value is just going to go in between the addition. So it's just going to be the sum, k goes from 0 to infinity, of the expected value of k to the x, s to the k over k factorial. But again, expected value is linear, so that's just a constant. That's not a random variable, right? That's just some number with respect to this expectation function, right? It's just a constant. So this is the sum, k goes from 0 to infinity, of the expected value of x to the k times s to the k over k factorial. Okay, great. But how does this give us this property? Why is it doing that? So the way to see that is you actually just write it out. Like, let's just actually write it out. So it's going to be k equals 0. We're just going to get 1, right? It's going to be 1 plus, because s to the 0 is 1. Expected x to the 0 is also 1, so expected value of 1 is 1, so we're just going to have 1. Then it's going to be expected value of x times s plus the expected value of x squared times s squared over 2, because the factorial, plus the expected value of x cubed times s cubed over 6 plus ... right? That's just going to keep going. Now think about what's going to happen when you take the derivative of this. This is your m This is your mx. Okay. What's going to happen when you take the derivative of it? Let's look at it. Mx of s, but prime, right? We're going to take this whole series, and we're just going to take the derivative term by term. Okay, so first of all, this goes away. It's a constant. This goes away because it's just s. And then you have a bunch of terms, right? You have a bunch of terms. But all these terms all have s in them. All have s. So if you then evaluate this at s equals 0, these terms go away. And all that's left is the expected value of x. So the derivative of the moment generating function is the expected value of x. Okay, great. But what if you take the second derivative? So what if we look at m? So again, I'm going to look at m prime. So m prime, just for a second, I'm going to look at m prime here. How about I just look at this? So again, the derivative, this goes away, but I'm not going to set this to 0 just yet. This goes away. And then we're just going to have, so that's going to go there. The s goes away because derivative of x is 1. And then this goes here, so this is going to be the derivative of s squared is 2s, so it's going to go away there. This is going to be s squared over 3 because the cube is over 2. I mean, cube is going to go down. And derivative just product power rule. Just doing that. It's a polynomial. It's a polynomial, right? Product rule. Okay, and now if I take the derivative of this again, this is just a constant. That's just a number. Derivative of s is just 1, so the s goes away. And we have a bunch of terms here again, right? But they all have an s in it. All have s in them. So if I evaluate this at s equals 0, all that goes away. And all that's left is if you take the, sorry, it should be clear, evaluate at s equals 0 here. You take the second derivative, evaluate at s equals 0, all that's left is the expected value of x squared. And hopefully you can see how this would just continue. If I take the fifth derivative and evaluate it at s equals 0, then I would just get the expected value of x to the 5, because all those terms would go away and all the earlier terms would be derivative of constants, so we'd have that. So that's what this is kind of saying. We have some random variable, and I want to find all the moments of it. I can get this function, and this function I can just get all the moments from it. This is the moment generating property right here, and we can do that, and we can find all the moments, all the expected values of all these things, relatively easily. Depends on how complicated x is, right? Depends on how complicated x is, but relatively easy. No integrals. Well, I guess maybe finding the moment generating function can take an integral, or it's just given to you. So let's do an example. Let's do an actual example. But hopefully that made sense. Demo. So let me find an example. There we go. Ignore that 6. 6 there. Chapter 6, I guess I meant. Yeah. So the moment generating function of a random variable x is all that business, right? And we want to find the expected value of x and the variance of x. So the expected value of x, right, is, like we just discussed, it's going to be the derivative of this MGF, so mx, or I guess it's phi s for some reason here, right? But evaluated s equals 0, and that's exactly like we just discussed this property here, right? That's what it's going to be. When you take the derivative and evaluate s equals 0, you get, and then the variance, right, of x is the expected value of x squared. I always forget, x squared minus the expected value of x squared. So this we'll just get from the previous step, and then this, right? Well, the expected value of x squared, that's just the second derivative evaluated s equals 0. Right? The second derivative evaluated s. Now it's a little bit of a messy it's messy derivative, so I'm not going to do the whole thing, but let's just at least find expected value of x. So phi s is e to the s over 2 minus e to the s squared. So now we got to find the derivative of it, right? We got to find phi s d ds. So, okay, so how do we do this? A chain rule, so 2 times e to the s over 2 minus e to the s, and then times the derivative of the inside. So the derivative of the inside is a quotient rule. So derivative of the top times the bottom minus the top times the derivative of the bottom. The derivative of the bottom is negative e to the s. All over the bottom square. And remember, this kind of looks scary, like it's just a bunch of just messy. But we're evaluating this at s equals 0. So that's why it's kind of convenient here, because it's going to be 2, 1 over 2 minus 1 times 1 times 2 minus 1 times negative 1 all over 2 minus 1 squared. This is 2 times 1 times 2 times 1 plus 1 over 2 minus 1 is 1, 1 squared is 1. This is 2 times 2 plus 1, right, which is 2 times 3, which is 6. That's not the answer I got before, so somewhere I made a mistake in here. 2 minus, what did I get before? I got 4 before, but did I just do it wrong? Yeah, I mean, maybe, I don't know.
You have an extra 2.
Do I?
2 times 1 times, you put 2 times 1 plus 1. I think it's supposed to be
1 times 1 plus 1. Yeah. 1 times, yeah, why would I write 2, 2, 1, and then 1. Yeah, I don't know what I was doing. Okay, perfect. That is the answer. This is going to be 1, 2, which is 4. There you go. So that is the expected value of x. Okay, that is the expected value of x. What you would do to find the variance is you need to find the expected value of x squared, right? So you would take the second derivative, like you take the derivative of this again, right? Which is a little bit of a pain, so I'm not going to do that. But actually it's not horrible, but it's pretty bad. It's pretty bad. So I'm not going to do it, but hopefully understand how you would do it. Take the derivative of this, and then evaluate it at s equals 0, and that would get you the expected value of x squared, and then you would put that into this formula to find the variance. I hope our formula sheet is good too. Yeah, I asked him if he could send the formula sheet today, and he responded tomorrow period. Tomorrow period. That's the whole email. So he seems a little unhappy about people asking. So, but it's fine. Okay. Let's see what's next. So I've done moment generating functions. This guy. We could do central limit theorem. Yeah. Yeah. Everybody just email him and get him more upset. This is on the record, so I'm joking. Let's do CLT, and then bivariate normal distribution, and then Poisson process. Probably that's a good order. All right, so let's do central limit theorem. Let me find an example. Yeah, okay, let's do this one. This is a homework problem. Am I too zoomed in? Oops, what happened? Why did I zoom in? No, am I not zoomed in? No, I think I'm not. Sorry. This is there. Okay. So 50 students live in a dormitory. The parking lot has a capacity for 30 cars. Each student has a car with a probability of a half, independently from other students. Use the CLT with continuity correction. Find the probability that there won't be enough parking spaces for all the cars. So we want to, what did I say? Yeah, if, so xi is the result of if student I has amount of cars student I has. Yeah, amount of cars student I has, which is xi is, you know, it's just 0 or 1. That's our assumption here. So xi is a Bernoulli distribution with a probability of success of a half. There's only one trial. They either do or they don't, and it's a half 50% chance, independent of other ones. So our total, right? Our total here, x, which is x1 plus x2 plus x3 plus plus x50, because there's 50 students, right? 50 students, is the total number of cars that we have, right? And we want to know, right? What's the probability that x is greater than 30? Or in other words, yeah, x is greater than 30. Right? That's the probability we're trying to find. What I can do is I can divide both of them in here by the number of students, right? The number of students. So I can say this is equal to the probability that 30 over 50 is x over 50 is greater than 30 over 50. Now, why would I want to do that? I'm basically talking about a proportion here. I'm saying the proportion of students that have a car is greater than this proportion. Okay, but again, why this seems like we're overcomplicating things. Let's look at what x over 50 is. X over 50, right, would be this over 50, which is the definition of what the sample mean is, right? So that's kind of our like y hat or x hat, I guess, x hat. Right? That's the definition of what the sample mean. And what the central limit theorem tells us is so one thing I was supposed to do first, and I'll correct that in a second. So the central limit theorem tells us is that this will be normally distributed with a mean equal to the mean of this guy. So what's the mean of this guy? So the mean, I'll say mean I is a half, and because it's just equal to p, and then the standard deviation or the variance is p times 1 minus p. That's the formula for this. So it's 1/2 times 1 minus a half, which is, you can't see it probably, which is a quarter. So what the central limit theorem tells us is that this will be this mu, the mu of this, right? So this is going to be normally distributed with mean of half and variance of 1 over 4 over 50. You just divide by the number of people that there are. So asking this question is the same as asking the probability that, x hat is greater than 3 over 5, which again, this is fine to do because this is normally distributed. So we can use the phi table for this. But there's one thing I'm forgetting. I said use with continuity correction. So basically, this is not a continuous situation, right? The outcomes are discrete. We're using a continuous distribution to try to describe this discrete situation, and that's fine because there's a lot of samples, right? There's 50, which is quite a bit. But it's still not exactly correct. So like this is it's approximately normal. So there's just something we can do to make it a little bit better. And what that is instead of using 30 here, we just subtract off a half. But you do that before you divide. You just subtract off a half from the bottom. And if we had a top limit, you'd add a half to the top there. We don't have a top limit this time. So I'm going to say this is, so actually I can't. This is going to be 30 minus a half over 50. So that's the continuity correction, this little guy. That's the continuity correction. and that too. So yeah, so at this point, we can just use our knowledge of how normal distributions work, right? So this is just going to be, well, I need to do 1 minus, or do I need to do that? Yeah, 1 minus the probability that, x hat is less than 29.5 over 50. Okay. So this is 1 minus the probability that z, so this is normal, right? So z is less than, okay, so I gotta take this 29.5 over 50. I gotta subtract off the mean, right? Which is half. And I gotta divide by the standard deviation, which is the square root of the variance. What was the variance? The variance was 1 over 4 over 50. 1 over 4 over 50. So that's some expression, right? This is, sorry, less than this. My calculator. I don't have my calculator, so I don't know what that is, but it's some number, and you could look it up in the table. Okay, yeah, sure, 1.273. And then you could look this up in the table. So this is 1 minus phi of 1.273, and we would just find that. We would find it. Thank you, Hanan. So yeah, that's how you'd solve that problem there. I should check if that's right. Let me check. This question. Yeah, we changed x bar to z because what we did is we normalized it, right? Because I subtracted off the mean and I divided by the standard deviation. So that changes into it's now a standard normal. This process of normalizing, going from here to here, is changed. They aren't equal. X bar is not equal to z, but x bar minus mu over sigma is approximately this, which is, and it's close enough for our, like, it's pretty close. Yeah, we're treating them like they're equal, and this little continuity correction just makes it a little bit more accurate. Linearly interpolate, like, oh, to find this? I don't think so. I've never heard it mention that. And also the numbers are so close together. Numbers are so close. Mech, you had to linearly interpolate, right? I remember having to do that. They made us do. Yeah. Okay, so that's that. Do you guys want to see another another CLT question, or that's good for now? I'm good to move on. So, sounds good. So CLT is done. Let's look at bivariate normal distribution. So for this one, yeah, what did I want to do for this one? Oh yeah, the textbook questions are just crazy for this. We're not gonna be asked that. So we can do his lecture problem. Sure. Yeah, we have time with it. We could do his lecture problem, which is this. Or we could do, well, in his own review, he did, there was a question like this. What am I trying to say? Bivariate normal distribution. That's what I'm trying to say. Yeah, I mean, we can look at it together quickly here. What are the questions? I mean, they're just crazy. So that's chapter 11. So chapter 7. Oh no, this is chapter 5 actually. I'm sure, yeah. You believe me, I know. So it's at the end here. It's not that one. I think it's actually just number 38. Oh no, sorry. This one wasn't crazy. Sorry. This one wasn't crazy. What am I thinking of? I'm thinking of something in chapter 6 was something crazy. This one was actually okay, but to be honest, it's kind of just plugging things into a formula. And we just need to know the formula. I think we should, like, what do you guys think? Should we do the lecture problem or should we do? I think the lecture problem is more similar to what we're gonna, if we were to get something, because that's what he wrote himself. I mean, he didn't write it himself, but he wrote the solution to it himself. So Any suggestions? I think this makes more sense to do. But like this problem, it's really just plugging in numbers into a formula. Very little time. Okay, I got one person agreeing with me, so I'm gonna go for this. Okay, sure. Yeah. We do have time, so let's do this one first, I think. So, at a measuring station for air pollutants, the amount of ozone and carbon particles are recorded at noon every day. Let X be the concentration of carbon. So X is carbon. Y is ozone. And suppose that XY has a bivariate normal distribution such that X is normal, 10.7, 29, 0. And Y is normal, 0.1, 0.02. And rho is 0.72. So rho is just a number, the correlation coefficient, that describes how what's the word, how related to each other, I guess, the two distributions are. So if on average, when X is high, Y is also high, and when X is low and Y is also low, if on average those two things match up, then the correlation coefficient will be high. But if on average, when X is high, Y is low, and when Y is low, X is high, if they're opposites, then their correlation coefficient will be negative. But if they're kind of just in between, it's just zero, right? Not correlated. And in fact, independent distributions will be fully not correlated. The correlation coefficient will be zero for independent distributions. So it's just a way to measure kind of how, there's a word that I'm trying to say. Coupled, I guess is what I'm trying to say. I'll couple the two. So, but anyways, to be honest, it's just part of the formulas, bro. So ozone level is considered unhealthy if it exceeds 0.3. So we're going to use that information. Suppose that the equipment used to measure ozone fails. So we're not able to measure the ozone, but we can measure the carbon, right? The carbon is 20. So X, I guess X equals 20. So what is the predicted ozone level and the probability that the ozone level is unhealthy? So we're looking for what is the expected value of Y given that X equals 20. Right? That's what we're trying to. So this is a conditional expectation problem that we have to deal with here. Right? So let's try to deal with it. So if I remember correctly from the lecture, this is the integral over Y. So we're going to integrate over Y. Integrate over Y. So we're going to do the expectation basically, right? But we're going to do the expectation of Y, Y dy, right? And what we're going to put in here is the conditional probability PDF Y given X equals 20 of XY, or of just Y actually, or of XY. Sorry, of XY. Yeah, I guess Y given X of XY. And we're setting the value of X equal to 20. That's what it is. Recalling how I did this earlier. So we know X equals 20, but we're going to use this probability distribution, right? Which is the conditional probability distribution of Y given some particular value for X. We're going to plug X equals 20, but in a second. And we're going to integrate this like we do expectation, just how we normally do it. So, okay, but what is this probability distribution? Like, we don't have that. Well, this is going to be the integral from negative infinity to infinity of Y. Okay, so this is the probability. This is fxy over f x. X equals 20. Right? This is x equals 20. Y. So this is just how conditions work, right? So this is like the conditional law, which is like the probability of A given B is the probability of A and B over the probability of B. That's what I'm doing here, right? So probability of Y given X is the probability of Y and X, right? Over the probability of X, which we're going to plug in X equals 20. There's a dy here. It didn't, yeah, sorry. Made a mistake. So now let's look a little bit carefully at what's going to be happening here, right? So fxy, right? fxy, these are independent, right? Or are they independent? The concentration is bivariate. Oh, they're not independent. Sorry. Yeah. Sorry. They're not independent. But so I was going to separate it out, but we effectively can. So why is it not independent? Are they independent? Not necessary.
Don't we know that they're not independent because of the fact
Because there's a row. Because,
yeah.
yeah. Makes sense. Yeah, that makes sense. Okay, so there's just an equation to use for this, right? There's just an equation to use for fxy, this thing up here, right? There's an equation. So what is all this, right? So this is kind of representing our first distribution with x. This is representing our second distribution with y, and this is for the bivariate normal distribution. So we know that we're plugging in x equals 20, right? Oh yeah, and sorry, one thing I forgot to mention is like these little symbols here, the hats and all this, right? These hats. There's just more equations to figure that out, right? So the equations are sigma mu hat y, which is that guy, is mu y, the mean of y itself, plus rho times sigma y over sigma x times x minus mu x. So we know all these numbers, right? We know that's given to us in the question. Come on. Given to us in the question. 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 That's 20. Given to us in the question. So we can find that number. And then we also have sigma y hat, which is sigma y 1 minus rho. And that tells us our two different parameters here of this distribution. So now that we have this, we can plug it in if we want to, but we're not going to do that. It's going to be a mess. Every other parameter we have in here. So if we look at what's going to happen, right? Yeah, according to... Right, just make sure I know what I'm talking about. So this top part, right? I guess we're going to kind of follow what he said here, right? So this label, you can just think of this like this is A1, right? This is the first bit, and this is A2. And so we can think of this as just relabeling here. This is just A1 times A2. And think about what A1 is going to be, right? A1, we know X. We're going to set X equal to 20, right? We're going to set X equal to 20. And so we're going to get just some number here. And then on the bottom here, this is that fx, the marginal PDF of x itself, equaling 20. And that's going to be this as well, at 20. So basically, this part of this is going to cancel out with that. And so all that's going to be left is the integral of, right? It's going to be that now just that integral of, of y times 1 over, sigma hat y root 2 pi e to the negative y minus mu hat y x squared all over 2 sigma squared y dy. But look at what we're saying here. This is exactly just the expected value of y, right? That's just the expected value of y here, which is from the question, or from the, oh no, wait, hold on. Is that the expected value of y? This is the expected value, not of y. Sorry, this is the expected value of the normal distribution, so a normal distribution. Let me open up his lecture, make sure I know what I'm saying. This was lecture Anyone want to take a guess? This is lecture 10. Okay, so when x equals 20, yeah, okay, so sorry. So let's calculate, like, we got to calculate what mu hat is and sigma hat mu hat y is and sigma hat y is, because that's in this here, right? There's so that's x equals, there's not supposed to be an x here, sorry. Why is there an x there? Oh, of x, right? That's a function of x. So I'm not going to write the function notation just because it's going to get confusing. This is a function of x, but we've selected x. Okay, so once we choose these, right? Once we figure out these, I mean, this mu hat y, sigma hat y, this is just finding the expectation of a normal variable whose mean is mu hat y and variance is sigma hat squared y, which is just mu hat y. So our answer to the whole question is just going to be mu hat y. And we have a formula for that, right? Where is it? That's our formula. You plug in numbers, right? So we can try, or just like believe me that it's going to be 0.2758. Actually, just believe the professor, actually. And to be honest, we don't even need this, right? Because if we just look at what we're doing here, right? This is the formula for the expectation of a normal distribution with these specific parameters here. And so we can do that. And then that's just going to be mu hat y. And that's going to be our answer for it. That's the expected value. Yeah. 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 That's correct. This is equal to that. I'll just like they're not independent. They're not independent. So it is weird that they cancel like that. They're conditional probability distributions. Well, it's not exactly that they cancel, right? Because this cancels with, so like this does, okay, sorry. So they do cancel. This part cancels with this, but that doesn't mean that they are in, can you review mu hat? We will be provided this equation. I mean, yeah. We will be provided these three equations, I'm sure, if there's a bivariate normal distribution question. So I think I understand what's going on here. So this does cancel with this part, right? But this is not exactly the PDF of y, right? It's the PDF of this kind of altered y, where we have a slight change because it itself is a function of x. This value is a function of x. So it's not exactly that they're independent, because you don't just get y here. You get something slightly changed from y because this equation function of x. Yeah. So anyways, there's that part of, this is the x part and this is the y part. So there's still part B, which is the probability that the ozone level is unhealthy, right? So we want to do part B now. I didn't calculate, whatever. Okay, I guess I did calculate. So that's the answer. Part B is probability that the ozone level is unhealthy. So what was our measurement of ozone? Ozone is Y, and the amount is 0.3. The ozone level, yeah. Normal distribution. Oh yeah, okay. Thanks. So y, we want the probability that y is greater than 0.3 given that x equals 20. right? Because we were given that information that the amount of carbon is 20, and y, it has to be greater than 0.3. That's the probability that the ozone level is unhealthy. So we do that. Let's see what that is. So again, how does he do it? Let's see here. Yeah, so he does basically the same thing. So he takes this. What does he do again? This is. Yeah. Yeah, okay. So. Yeah, okay. I think I understand. This is the integral. We're looking for probability that y is greater than 0.3, right? Y can go from negative infinity to infinity. It's normal. So it's going to be y greater than 0.3 is 0.3 to infinity. This is going to be dy, right? And what we're going to do is we're going to multiply, we're going to integrate f y given x, and specifically at x equals 20 dy, right? That's going to be this. And this takes into account that idea that x equals 20. But this is exactly what we were saying before. That's exactly what this distribution is. This is y, but you're taking into account the x value, because this is a little function of x here, right? That little mu is a function of x. So this is equal to the integral from 0.3 to infinity of, this 1 over sigma hat y, lowercase y, root 2 pi e to the negative y minus mu y hat squared over 2 sigma hat y squared again? No, not squared again. I can't. Oh yeah, sigma squared here, dy. But this again is exactly the probability that this altered y, which means we've taken into account this, right? Probably this y hat, it's not the notation he uses, but this y hat is greater than 0.3, which is, this is normal, right? This is normal. So probability that 1 minus the probability that this y hat is less than 0.3, which is 1 minus the probability that z is less than 0.3 minus mu y hat over sigma y hat, right? Because this is a normal distribution, but with these particular properties here. And we know all these numbers, right? We know less than 0.3 minus whatever we set up here, 0.2758. And sigma y, just, he did it. It's the formula here, right? Just plugging in this formula. We know all the numbers. It's going to be, so square root of 0.0096. And this is figure outable, right? This is just, you just use the table for that, right? So that's kind of the logic here, is that we set up this integral with the conditional PDF, conditional distribution, and then from here we use that conditional distribution here, right? That's exactly what we're describing this as, and then call that, this is what we're doing here really is find the probability of this. This is normal though, right? We know this integral. This is represented by this. This is a normal distribution. This is the CDF. And then we rearrange it, use that normalization property here to switch it to the table, and then we have it. So yeah, that's that. So I will check that off our list. Let's finally, let me drink some water. So let's just finish up, make sure we get everything done, right? Let's do a Poisson random process. And if you have time after, we'll do some more. About 23 minutes, so time. So let's see what is. So where are we here? So I have a few options. I mean, we can do this textbook problem, I guess. And then there you can do a textbook. And what might be good for us to do as well is that he likes to use textbook problems that he didn't assign. I've noticed that in the past 2 midterms. Like it's just like the next question that he didn't assign that, so he probably didn't do it, right? So maybe we'll just scan through, see if there's anything interesting. Obviously, there's something too complicated, but yeah. Okay, so let's try this question here. So 2 teams A and B play a soccer match. The number of goals scored by team A is modeled by a Poisson process, and 1 of T with a rate or an intensity lambda 1 equals 0.2 goals per minute, and the number of goals scored by team B is modeled by a Poisson process, and 2 the rate lambda 2 equals 0.03. The 2 processes are assumed to be independent. Let n of T be the total number of goals in the game up to and including time T. Long day. And the game lasts for 90 minutes. So A is find the probability that no goals are scored. So we want to find the probability. Yeah. Okay, so the goals scored by team A, so I'm going to call it XA, right? The goals scored by team A. Team A, right? And XB, goals scored by B. So basically, we want to know what's the probability that after 90 minutes, right? I guess I should say, yeah, after 90 minutes. After 90. Probably that XA plus XB equals 0, right? Equals 0. Because no goals are scored. This means, how do we do it? I remember how we did it. This is, yeah. This means basically that this implies that, yeah, exactly. Yeah, that totally works for this one. So this implies that this is the probability, this is equal to the probability that XA scores 0 goals and XB, or team B, scores 0 goals. They're independent, so this is the probability that XA equals 0 times the probability that XB equals 0. Okay, but what's XB? Well, XB is a Poisson, like it's a part of a Poisson process, so it's going to have a Poisson distribution. What's lambda going to be? Well, lambda, right? Lambda, or yeah, let's open up the actual thing here, right? Make sure. The number of arrivals in any interval of length, tau greater than 0, has Poisson lambda tau distribution, right? Lambda 1 tau, and this has a Poisson lambda 2 tau distribution. Tau is 90 minutes, right? And lambda 1, is it the right units? Lambda 1 is goals per minute. Lambda 2 is goals per minute, right? So this is going to be Poisson, where that's a 1. Lambda 1 tau, lambda 2 tau. So this lambda 1 tau is equal to 0.02 times 90, right? It's 0.02 times 90, and then 0.03 times 90. 0.03. That's the lambda 2 tau. Some number. Oh, my calculator again, so I don't know. 0.02 times 90 equals 0.8. So equals 1.8. And then this is 0.03 times 90. So what does Poisson look like? Well, it's, if I remember correctly, e to the negative lambda to the k over k factorial. K is the number of goals, so that's 0 in R, right? That's 0 in R. Times e to the negative, I should be clear, this is like lambda 1 tau, lambda 1 tau, lambda 1 tau, e to the negative lambda 2 tau, lambda 2 tau to the k over k factorial. But again, 0, 0. So this is just e to the 1.8 or negative 1.8 times e to the negative 2.7. That's the answer. So hopefully that makes sense. Here, like that. That's part A. Part B is find the probability that at least 2 goals are scored in the game. Probability that at least 2 goals are scored in the game. So that means that we're finding the probability that XA plus XB equals is greater, at least 2 goals. So it's greater than 2. Or greater than equal to 2. Yeah, at least 2 goals. So this is equal to 1 minus the probability that XA plus XB less than 2, which is 1 minus, okay, well, what are the cases here? Either XA scored no goals and XB scored no goals, or XA scored a goal, but Team B didn't score a goal, or Team A didn't score a goal, but Team B did score a goal. And there's no other cases, because otherwise there's more than 2 goals scored in the whole game. And so we just find each of these probabilities the same way we've been doing it. We already said this is e to the negative 1.8, e to the negative 2.7, right? That first term. And then the next term, right? This is going to be e to the negative 1.8 times 1.8 to the 1 over 1 factorial. Because it's lambda 1 tau to the k over k factorial. So that's for this term, doing this term. Times e to the negative 2.7, because that's the other lambda for the other variable. 2.7 to the 1 over 1 factorial. Plus, and then here we have e to the negative 1.8, oops, 0 and 0. E to the negative 1.8 times 1.8 to the 0 over 0 factorial times e to the negative 2.7 times 2.7 to the 1 over 1 factorial. And there's some stuff to work out here, right? But that's it. That's the that's how you come to the conclusion. You can consolidate into a single lambda for these questions, so you can just say, yeah, that does make sense, because e to the negative lambda 1 tau to the k over k factorial times e to the negative lambda 2 tau to the k over k factorial, which is just the product we're making, is equal to e to the negative lambda 1 tau, or what did you write? Yeah, lambda 1, whatever. Lambda 1 tau plus lambda 2 tau, lambda 1 tau plus lambda 2 tau to the k over k factorial, which is a Poisson distribution with lambda 1 tau plus lambda 2 tau. So yeah, you can do it as just one distribution. It would be the exact same answer. But yeah, that makes sense. Okay, that's part B. And then part C is find the probability of the final score being that. So that's not too hard, right? Find the so we're looking for probability that XA equals 1, XB equals, what was it? 2? Which is, we just saw this, right? So e to the negative 1.8, 1.8 to the 1 over 1 factorial times e to the negative 1.8, 1.8 squared over 2 factorial.
Shouldn't it be 2.7?
It should be 2. That's right. There you go. Thank you. So that's it for C. And then let's see. Part D is find the probability that they draw. Oh yeah. So this one's weird. Did I actually finish this? Let's see. Oh yeah, we have it written as like not as a nice number, just as an infinite series. So the probability that they draw, I'm not gonna spend too much time on this if we can't figure it out. The probability that they draw is the probability that XA equals 0 and XB equals 0 plus probability that XA equals 1 and XB equals 1 plus probability that XA equals 2 and XB equals 2 and so on. So okay, let's try to find it, right? So what would this be? This would be so I'm just going to leave it as, how should I leave it? Okay, I'll leave it as, okay, I'll write it. So e to the negative 1.8, and I'm not going to, it's just e to the negative 1.8 times e to the negative 2.7, right? That's all that would be for that one. Plus e to the negative 1.8 times 1.8 over, well, not even over 1, just that, right? Well, I guess, okay, over, yeah, okay, I guess I should write everything. So, I'll, okay, I should write everything. So this is going to be 0 factorial, and this is 1.8 to the 0. This is 2.7 to the 0 over 0 factorial. Obviously, I didn't change anything there, but just to see the pattern, right then. Oh, I guess we don't need to see the pattern because we know in general this distribution. Yeah, so in general, I guess, okay. In general, yeah, you know what? There's a better way to do it. We can just do it. We can just do it like that. So we're looking for the we have to understand what the probability is. Probably that XA equals N, XB equals N, right? That's what we're trying to figure out. So what is that probability? That's probably e to the negative 1.8, 1.8 to the N over N factorial times e to the negative 2.7 times 2.7 to the N over N factorial. So we want to take the sum of this, right? Our answer to our probability is it's the sum for N goes from 0 to infinity of exactly what I just wrote here, right? E to the negative, well, I'll just copy and paste it over. And it looks like it should be some e to the something, but I couldn't figure out how to get it to that. So we can try it. So we could say e to the negative 1.8, e to the negative 2.7 times the sum. N goes from 0 to infinity. And then you could say 1.8 times 2.7 to the n over n factorial squared. N factorial times n factorial. N factorial times n factorial. Whatever 1.8 times 2.7 is. 1.8 times 7 equals 6. So this is the sum. N goes from 0 to infinity of 4.86 to the n over n factorial squared. So the weird thing is that we have n factorial squared on the bottom. It's almost e, but it's not e. This is almost e to the 4.86. Oh, sorry, I forgot the. I would say lab problems are probably the best thing to do. Not that he's gonna exactly put lab problems on, but I think they're more related to the content. A lot of the time, the suggested problems are just something crazy, and his tests are not crazy, right? So that's the simplest I could get it. I don't know. Lecture problems are good too. Absolutely, they are good too. So I'm definitely gonna spend some time studying lecture problems. Because there's one thing. You have a feeling you'll ask this one? Yeah, like the series. This like doing this. Maybe. So we better figure out what this is. I have no update, but if I figure something out, I will let you guys know. I have no update. Okay, so then there's one thing I forgot. Two people actually asked to do for me to do a question, problem 18 here. You don't have to do the same, the whole thing, but problem 18. Actually, two people asked me specifically to do part E. So let's do part E. We have two jointly, like x and y be two jointly continuous random variables with joint PDF. Find that, whatever. So here's our, I'm just going to sketch it. I say whatever because like it doesn't mean anything if I just say it, so I'm just going to draw it. So x goes from -1 to 1. Y goes from 0 to 2. So this is our zone. Right? So I want to know the probability. I'm doing just part E. Part E is the probability that x plus y is greater than 0. Probability that x is greater than -y. Or I guess probably a better way to say this is move the x over, so y is greater than -x. So -x looks like this, right? That's 2, so it's going to be, yeah, so not going to go in this corner, is it? Because that's the point. No, it's not going to. It's going to go like, yeah, 1, height of 1. It's going to go like there. There you go. And I don't care about outside the box, right? I don't care about outside. So it's going to go through the point 0, 0, that line, and it's going to go through the point, like y equals -x. That's what I'm drawing. Y equals -x. And it's going to go through the point -1, 1. So we care about where y is greater than this, right? So where y is greater than this, so that's this whole section. We don't care about outside the box at all, right? Because that's where probability is 0, but where probability is not 0. So this line does continue like this, right? And so we care about this area, but not in this section. So now we want to find this probability, right? We want to integrate this function over this region. So this is going to be the double integral. So I'll do, I don't know, I'll just do vertical differential element. It's going to be two integrals, right? It's going to be an integral in this zone, and it's going to be an integral in this zone, right? So I'm just going to call this area 1, and this is area 2. So for area 2, it's just the integral x goes from 0 to 1, y goes from 0 to 2 of our fxy xy dx. So I said x goes from 0 to 1, y goes to 0 to 2. So that's area 1. And then that's area 2, I mean. So maybe I should call this area 1. Call this area 2. So area 2 now is, this is the double integral again. So y is bounded between -x and 2, and x is bounded between -1 and 0. F xy xy dy dx, because y is bounded between these two. So then you can just work it out, right? You can just work out what this is. So 0 to 2, integral 0 to 1, 1/4 x squared plus 1/6 dx dy plus integral -1 to 0, -x to 2, 1/4 x squared plus 1/6 y dy. So we can do it. Find questions related to setting up these wonky integrals. I mean, there's the textbook from MTH514, right? MTH 312. Where is it? Advanced. There it is. There's this textbook, which is good, and it has a lot of, vector calculus, and then like double integral. So it talks about setting up these integrals a lot. So that textbook. If you wanted, you can message. So let's just integrate this. I mean, we only got left, so integral 0 to 2, integral 0 to 1. Okay, well, I guess I'll get rid of 1. So I'll do dx right now. So it's going to be 3 over 4x cubed plus 1 over 6yx evaluated 0 to 1 dy plus integral 0 to 1, negative 1 to 0. So I'll integrate this dy right now. So it's 1 over 4x squared y plus 1 over 12 y squared evaluated negative x to 2 dx. Integral 0 to 2. Evaluate this at x equals 1, right? At x equals 1. So it's going to be and 0 doesn't matter. So it's just going to be 3 over 4 plus 1 over 6y dy plus integral negative 1 to 0. Evaluating this at y equals 2. So y equals 2. This is going to be 1/2 x squared plus 1/3 dx. And then dy, it's going to be 3 over 4y plus 1 over 12y squared, evaluated 0 to 2, plus, and then this is going to be integral dx, so it's going to be 1 over 3, 1 over 6, x cubed, plus 1 over 3x, evaluated negative 0. Evaluating at 2, this is going to be 3 over 2 plus 1 over 3. Evaluating at 0, we get nothing. And this is going to be evaluating at 0, we get nothing. Evaluating at, and then evaluating at negative 1, this is going to be negative 1 over 6, and then minus 1 over 3. That just goes away. But we're subtracting that. So we're going to subtract this. So this is going to be 3 over 2 plus 1 over 6 plus 2 over 3, which I don't feel like computing at the moment. This is, I don't know, 1 point, some number, right? Bigger than 1, so that's an issue. But yeah, bigger than 1. So let's type it into Wolfram. See if it's just an issue I did in integration. I missed the negative sign somewhere. That's it to Wolfram. Let's type it in from here. So it's the double integral 0 to 2, 0 to 1 over 4 x squared 1 over 6y negative 1 0 negative x. What did I do? Yeah, what did I do here? Let's just type it in anyways. Make sure. Yeah, just almost done typing it in. So yeah, I see what mistake. 1 over 4 x squared plus 1 over 6 y dy dx. Just want to make sure we get a number less than 1. Yeah, 0.9. Why did I just ignore? I just ignored the bottom bound here. I thought it was 0 for some reason. So this is not that. So it's going to be minus, evaluating at negative x, so it's going to be 1 over 4 x. Oh, yeah. Hold on. What did I just do? Wait, evaluating at y equals negative x. So it's going to be minus negative 1 over 4 x squared x plus 1 over 12 x squared dx. this term's wrong now too. Integral negative 0. Anyways, this doesn't particularly matter. Like, just you can see what it is. It's 1 over 4 x cubed plus 1 or minus 1 over 12 x squared. Anyways, believe me that this works out. I mean, it's not a complicated integration after this. It's just, believe me that this works out to 0.90972. There we go. So hopefully that made sense for part E, how to do that. And that's our time. It's 8:03. So I hope everybody feels good about the stuff we covered today. If you have any questions, you can ask me over Discord or whatever. Over the bounds, yeah. So this integral is for region 1. No problem, guys. Region 1, just a rectangle. So x goes from 0 to 1, y goes from 0 to 2. That's not interesting. Region 2, A2. Okay, think about a little line here, right? Y is bounded between what two numbers? Y is bounded on the top by 2, on the bottom by negative x. That's what it's bounded by on the bottom. And then y this little line, I mean, can just vary between -1 and 0, right? Just in this region, just in this A2. So that's why -1 is 0 and negative x is 2. So you see x in total is going between -1 to 0, 0 to 1. Out of all the branches of math, how much do I enjoy stats? Probably. I really enjoy it. This course, like, less than the actual stats. Like, I took a statistics course in the spring, and I really loved statistics. This is like a little bit more heavy on the theory, not getting into like why would we need to know all these PDFs and CDFs and all that kind of stuff. So the statistics course at the end, like we did do like some more practical things. Still pretty theoretical, but more practical things, and that was really interesting. We did like hypothesis testing and maximum likelihood estimators, so like whatever. So it was yeah, it was interesting. So I do enjoy it. I think it's pretty cool. And yeah, okay guys, well, I'm wrapping up. I'm gonna stop recording. See ya.